Okay, this is a quick video on making sure the chain rule makes sense to you. I've been in most of the videos where I've talked about taking derivative. I said you need to always be aware of the chain rule because there's often composite functions lurking in the midst of some pretty basic looking functions. So here's a writing out of the chain rule. Du dt is equal to du dx times dx dt times dd dt. Of course, this is equal to this is equal to 1, so I don't really need to write it. And this is understood where u is a function of x and x is a function of t. So that is kind of the formal way to talk about it. It probably doesn't make a lot of sense to you unless you see it in terms of an actual example. So let's go there. So let's say that we have f of x is equal to 3 times sine x squared to the third. So this is what we're talking about. So the u in this case, the u might be 3 times something cubed, and the x would be like sine of something, and then there's actually more layers than we have here. So then the next layer would be something squared, and then the final layer would be, so let's rewrite this as, layer 1, layer 2, layer 3, and then finally layer 4 is just x. Okay? So that's the example of a composite function. Clearly you can see that h is a function within another function. So there's several layers there. So what the chain rule says, you got to take care of it one layer at a time. You take the derivative of the outermost layer and leave everything else alone. So in this case we have h of x. Now I'm taking the derivative, so that would be the outer layer. I'm just dealing with this form right here. So that would just be the power rule. So that'd be 3 times 3 is 9. And on the inside, it's going to stay the same, and this will be drop from 3 to 2. So in here, I still have just sine of x squared. Okay, that took care of the first layer. Now the second layer is just sine of something. So what I'm going to do is multiply by the derivative of the next layer. Well, the derivative of sine of something is cosine of whatever the something is. Notice I didn't change the x squared. So that took care of the second layer. Now we're going to look at the third layer. The third layer is something squared. How do you take the derivative of something squared? It's 2 times the something raised to the first power, which we don't need to write. And then finally, the last layer is x. What's the derivative of x? That would be dx dx, which is just 1, so I don't bother writing it. So that would be an example of an extreme chain rule. Now notice that I got 9 times sine x squared times cosine x squared times 2x. Now I'm going to do a little bit out of here to make it write it in simplest form. I have a 9 and a 2 that I can multiply, so that's going to become 18. This x makes more sense to put it out front so I can see that it's just an x times, and then I'm going to have sine. Often it makes more sense to write it like that, sine squared times cosine x squared. Okay, so that would be my final answer in that case. So that's the chain rule when you got something inside of something. Now, the chain rule, like I've said many times, the chain rule applies all the time. So if I have something like sine x and I take the derivative of that, f prime of x, well, the outside layer is sine, so I take the derivative and I get cosine. Then the next layer is x. The derivative of x is dx dx, which is 1, so I don't bother writing it. So here's some more subtle ones. Let's say we have y equals 5 to the 3x. Sometimes that's hard for people to see that this is a function inside a function or a composite function. But really this is, remember, the outside function is 5 to the something, right? So then the inside function would be 3x. So if I take the derivative of that, dy dx, I get, well, the derivative of 5 to the something is natural log 5 times 5 to the something. Then I have to multiply that by the derivative of 3x, which of course would just be 3. So then we get 3 times the natural log of 5 times 5 to the 3x. And if you remember your log rules, you could rewrite that as natural log of 125 times 5 to the 3x. Because remember, 3 ln 5 is the same thing as ln of 5 to the third power, and 5 to the third power is 125. Okay, so just another example similar to that. What if we had like 3 to the x squared? Well, dy dx is going to be natural log of 3 times 3 to the x squared, because that's the derivative of 3 to the. Then I have to multiply that by the derivative of x squared, which of course would just be 2x. And then multiply that by the derivative of x, which of course the derivative of x is just 1, because it would be dx over dx, just 1. Okay? And of course you could simplify this to natural log of 9, because this would be ln 3 squared times x times 3 to the x squared. Okay? Great. One more example. Let's do natural log of x squared. First of all, the derivative of natural log of something is 1 over the something, so that'd be 1 over x squared. Then I have to multiply that by the derivative of x squared, which would be 2x. So that'd be 2x over x squared, which of course is simplified to 2 over x. Okay? So that's a pretty good example of just, so here's some chain rules, some fairly simple chain rules that are producing something other than just dx dx. Oh yeah, there's one more thing I want to say. Let's say that I have an equation that says y equals sine of t, for example. Okay? And let's say I want to know what the derivative of, I want to know what dy dx is. Now remember, the thing that I said I like about this notation is that this tells you, whenever you're taking a derivative, you're doing a rate of change. So you're comparing a change in something to a change in something else. So this is telling me that I'm comparing a change in y to a change in x. Now the problem is that my equation is in terms of t. And at this point, I don't know how t and x are related. So if I took the derivative of this, I'd have to write this as cosine of t. Then the chain rule would say to take the derivative of t, right? Because I took the derivative of sine, which was on the outside. But now I take the derivative of t. But I don't know what the derivative of t is with respect to x. So I would just write it as dt dx. Okay? So compare that to y equals sine of x. And if I take dy dx, well, I get the derivative of sine is cosine of x. Then I multiply that by the derivative of x, which is dx dx. And of course, dx dx is just 1. This is saying how is x changing compared to how x is changing? Well, they're changing the same. So it's a 1-to-1 correspondence, so that would just be 1. So it's just cosine x. All right.